So this is the end of last very long day. So and I don't plan to state any theorems, so she will be relaxed. And I just want to mention some proposal. And so this is the proposal. So I want to consider some compact simple manifold, but which has some toric type singularities. And the conjecture is that we can define a Fukaya theory of such singular simple manifold. And the main thing I want to explain is which kind of Lagrange submanifold we want to consider in this singular simple manifold. And this simple manifold is something that a toric type. And if I want to be a bit more precise, then so then let me consider this Fuqua story of something he called exponent manifold. That's something should be symplectic equivalent to log vector theory, and the conjecture is that it should be stated for this exponent symplectic exponent manifold with symplectic structure. I will mention what it is, but and I think one reason we can try to do this is that there's from a vector theory for long variety with long singularity, and also for exponent manifold with people ability, and we expect to have some Lagrange theory in similar situations, and that kind of thing should be useful. So, but the problem is which kind of Lagrange manifold is not natural to consider in such a spaces, and why this so I have to try to craft this rare theory. But I want to start with some very simple case. It appears in the joint paper with Alekam Daini, and we actually wrote 3 papers, another lengthy papers. That's a very easy case. Easy case means that we only consider compact simple manifold, which is in that paper we consider compact simple manifold and a smooth divisor, and we consider only Lagrange submanifold, which is away from this smooth divisor. So that's a kind of very rather easier case. So this case is not covered the previous work, because this divisor we don't assume any positivity or negativity. But still, so we need to do some many analysis, and we want to kind of make the paper shorter. It is already 200 pages, but we want to make it shorter as possible. So we don't want to go more. But at least to this stage, I'm pretty sure we can do it. So we didn't write it. So we need the following stations. We go to smooth defect manifold, that's for the major 2. Smooth manifold, so that restriction of the symplectic form is the restriction to D is the simple structure of W. So that's the usual case to do. In a Kerr category, that's a complex divisor. And we can prove that there is a compatible almost complex structure on X, so that there is a local fixed actions in a neighborhood of D. Local fixed action means that just the neighborhood 1 is active there, which preserves the critical complex structure. And then we fix that kind of structures. So we have this, and then we consider Lagrange submanifold L, which is a stability manifold with boundary, and the boundary is just a L-cap divisor. This means that this intersection is not transversal because they have a value 2, so but the boundary air has a value 1. And you can imagine a typical situation looks something like this. You have this L here, this point of divisor, so it's the boundary. And we assume that this, let me remind you, we have the cis actions in a neighborhood of D. So we cause the R plus positive real number in this sister, and we require this L which is invariant by this R plus action, so this kind of straight line goes there. And of course, that dimension, actually dimension is higher. So that's the kind of submanifold we want to consider in this first simplest case of smooth divisor. Then what we expect is suppose that we have 2 Lagrange submanifold, and because so then two of that and this kind of manifold, and we consider this L1 not is the interior. There are 2 kind of intersections. L1 node and L2 node, and also boundary L1 and boundary L2. Indeed, these two are Lagrange sum codes, Riemann construct intersections. And we require that at the boundary intersection point, these two have a non-trivial angle. So it means that you have this point. I'm sorry, we don't have enough dimensions, so just intersect this point, then these two somehow have non-zero angle, and this is not allowed. So we consider this kind of statement. So now, I think you are familiar with something like a rough Fourier theory, and then if you think it is a kind of positive divisor, you can consider this rough Fourier Morphy, and it means that this intersection point contributes infinitely many generators in this Fourier theory. But I want to do it in a bit different way. So first what I can do, so we consider this CF class, the temporal complex, is a free module of interior intersection point, and for this boundary intersection point, I'm sorry, this is P, not P. And we take this polynomial ring. We take another generator P, and so we take this. So we have this infinitely many generators. I think this is somehow related to this S1 actions. I mean, this P may be regarded as a kind of generator of H2BS1, and the Novikov ring has another generator which we call large T. So you have these two generators in a similar sense, like this one equivariant and the energy. And you have a CF minus, so that this positive power is replaced by negative power. And the conjecture, which is more realistic than conjecture I wrote at the beginning, is that we can define boundary operator of this positive and negative thing, so that it gets a chain complex. And so I just want to explain how we can define these boundary operators. So the boundary operator between interior mark point is rather easy to see, and the interior mark point is easy to see. So something which you need to understand is that you have an interior intersection point and boundary intersection point, and I want to define the coefficient for the boundary operator, which should be an element of polynomial ring. And so that is, we count this kind of thing. So P is the intersection L1 and 2 the interior, and Q is the intersection on the boundary. So we consider the answer this is Q. We consider the phi of Q of the normal particle, it's complex vector space, and we have L1 and L2 in the intersection of the normal particle. And let me remind, we assume that L1 and L2 is invariant of R plus actions. So I'm sorry, this is R plus. Yeah, I'm sorry, this is not R, this is R plus. It looks something like this. Its origin is this two half line, and we have a non-trivial angle which is a theta. So this is a theta. So I want to consider U, which is a holomorphic strip joining this P and Q, and it is boundary L1 and L2, and then near minus infinity it goes to P. I didn't close it. Yeah, but near the plus infinity. So this should go to Q. But if you look like how it behaves in normal values, then it is supposed to behave in this way. So it's something like theta is just from angle from here to here, but it may rotate many times. So this N is something like how much did this rotate until we arrive to 2. And if you know something about the relatively long Victor theory, we consider this holomorphic sphere so that it has some tangency on the beam. And this is very similar to that kind of definition. If you replace the tangency, we have these two lines, so we have about very many rotations. So we count this kind of holomorphic strip, and that is this AI, AN, and we take this polynomial. I think one can prove this is finite, only finite many times. We have this kind of polynomial. So that's the boundary operator from the interior mark point to the boundary mark point. I don't know, so in interior the boundary intersection. But then we need another thing. Suppose we have this. Suppose Q is the boundary intersection and P prime is the integer intersection. So we have to define boundary operator from Q to P. And that's something a bit linguistic theory, because the Q has a, in a sense, positive thing. So here, before this kind of relative mobility theory, it comes from outside to the D, but then you have to go deeper to D. So you just think very naively, there cannot be such a strip. But there is this kind of strip, you have a Q to R to P prime, and R is another integer mark point. So I want to explain what this figure means a bit more precisely. So this part is U1, and this part is U2. The U1 is a strip to D, because then is a divisor. And then the first part goes boundary L1, and second part is boundary L2. And then minus infinity is Q, and plus infinity is R. So this is something like to calculate a Fourier's boundary operator to Q to R in the secret manifold D. And then we put some extra conditions. So we consider the full back of the normal boundary, it's a complex line boundary. And we can assume that it's actually integrable boundaries. And so then we have L1 and L2. So this boundary of L1, normal boundary of L1 and normal boundary of L2 is a kind of positive real line boundary on this complex line boundary. So we require that these two. So here we have sections here, and this in each boundary they are required this real part. And then we also require at the start minus infinity plus infinity, and this section has a pole of order n and l prime. So n is so we have some n and l prime. So it's something like this, and the figure is like this. So you can use this S to reach this U1 to the mark to the total space of the normal boundary. Then this goes to infinity, and this goes to infinity, and you have this Lagrangian boundary. So this is the kind of picture for R. So this is this ends. We have something carried from order n and going to order n prime. And then you have this U2. So this is this kind of thing. Then I want to consider another part. That is U2. U2 is R strip to X, and if U2 starts from R, and U2 go to P prime. And also you assume this kind of thing. So this means that how this strip behave on R, and it's n prime. So this n prime is something like how this strip rotates near R. So if everything is nice, that we can try to glue this U1 and U2 at R. But we cannot actually glue, because after gluing, you have some very storage state coming back and going out. There's no such a configuration. So you cannot actually glue, but you can pretend that it's something you can glue. So this is the second picture. So let me go back. So we consider this kind of pictures. We consider this kind of pictures. You have U1 here, U2 here, and it is kind of glue. So this order n. So we can consider the case that this configuration is actually isolated. It depends on zero. And that is the definition of this Pn. And so you take this boundary Q to P prime is just sum of the n of this P to prime, P to the power n. Let us say, I mean, maybe T with the minus n is better, because if the boundary of P and Q is this Pn. The coefficient of boundary P and Q are P prime. So yeah, this is not so easy. Boundary of T and Q. Boundary of T and Q P prime. Maybe it is better to write it. So this is the definition. So I just want to mention. So this is the definition. So So we count this kind of thing as we count this kind of thing. This is plus, and we have a minus, then it's a bit strange, but we have this kind of thing and this kind of thing. So this goes from here to here, so this go up. So this, from P to R, you have this negative power of P. And this is going from here, you have another negative power of P. And this is some, there's a reason that we need to count this kind of thing. The reason is the following thing. So we want to study this strip between P and P prime. P and P prime is the interior intersection. And we want to prove that the boundary square is zero. Then you have to study the boundary of the moduli space of strips. Oops. What happened? Oh,
Yeah.
this is that my okay, yeah.
There. Okay.
Okay. So now we need to consider this we need to consider one dimensional case, and you have to consider the boundary of such a strip. And there is a space that the strip goes like this. And you know in your player theory, you see that this is the fundamental two. It looks like a fundamental two because we have a two boundary node, and this boundary node decrease dimension one. So this looks like fundamental two, but you think of it carefully. Actually, this happens to be fundamental one. So this is actually bounded. So you have to do something to cancel it, and you cut it here. This guy, if you cut it here, this guy corresponds to the composition of this guy and this guy. So you count this and this, then it cancels this boundary. And that's a proof of boundary square zero. And if the different way of cutting at a R, then you have this and this. This is another way to cancel this boundary to get something very fine. So this is an idea to define this player homology. And I say that this is actually not so novel. And a very similar thing appears in a study of the cybernetic player theory. If you look to famous book by Kroheim and Brook, they wrote basically the same features. In this case, that this divisor P is played by reducible S1 U1 reducible connections. So so this is very simple. And also have this Hegel player theory. And I don't remember Hegel player theory just hat and another hat, and you have this exact triangle. And that story is expected to exist in this divisor cases. Okay, so now this is the case we have this just one smooth divisor. And then I want to go to the next case that we have a somewhat unrelated case. Suppose we have a simple normal crossing divisor. So what is simple normal crossing divisor? You have a smooth symmetric manifold, and you have a D, it is a union of DI. And DI is again for dimension 2, symmetric submanifold. It means that it is a dimension 2 through submanifold if its symmetric form is not degenerate. And you have this index set I, and you have any subset, then you consider this intersection of Dj, that intersection is assumed to be transversal in obvious sense. And also, I think one needs to assume some positivity, and this kind of positivity is studied by these people, McQueen, Tekurani, so we have some assumptions. And under these assumptions, so we can generalize this construction of the sister actions. So the situation is something like this. You have a D1 and D2, and in the neighborhood of D1, as I mentioned, we have the sister actions, which is something like a obvious sister action in the normal boundary. And then in the neighborhood of D2, we have another sister action. And in the intersection of D1 and D2, these two sister actions are kind of weird. So you have this kind of situations. So you have this local sister K actions. And actually, this kind of structure is known in a theory of collapsively many manifold many years ago. And Chia Gromov called it a T structure. T structure is not sister only S1 part. It's a very similar kind of situation. So you have this normal crossing divisors that have many sister actions which commute in an overlap part. So we have this situation that we can define J. We can find almost complex structure J. So that this action is reserved here. And of course, compatible with the So now I want to consider some Lagrange submanifold L X. Then, so which kind of Lagrange submanifold is the kind of natural to consider in this context? Is the following. L is a smooth manifold which has a corner. So we consider for the dimension K corner of L. And for the dimension K corner is actually an intersection of this dj. J is a subset of order K of I. And if you take the intersection of dj, which is for the dimension 2K submanifold of X. And the intersection of L with this for the dimension 2K submanifold is for the dimension K corner of L. So that is the kind of natural submanifold which we can consider in this context. And also, let me go here, let's shift actions. And we require that L is invariant of the positive R to the power K actions in the neighborhood of this possibility K corners. So you have this kind of situation. That's natural generalization, the case K1. And then you have two of such a submanifold. Then we have to consider this Freire theory. So it means that this Lj has a codimension K corners Sj. J is the index set of order K, and you can just take the intersection of Li and J and Dj's. And so we have this Sj Li is a Lagrange submanifold of Dj. Dj is the intersection, J intersection of this smooth divisor. Then so we consider this generator, which is a kind of intersection of this polynomial K corner. And then we have generator, but in this case we take this polynomial ring of generated by Tj, J is an element of J. In other words, we prepare, this divisor is indexed by I, script I. So for each element of script I, we prepare one variables. And we consider this so Ti, I want to some number of dividers. Now, and then we for each P in this set we consider this Tj. We have this polynomial ring and on top ring. This seems somewhat reasonable, right? Because you have an action of sister J on this sister K on in the neighborhood of P, and you have taken in particular S1 to the power K acts there, and P in a point of divisor, the fixed point of this S1 to the power K. So this Tj is something like a parameter, maybe W2, which is related to the H2 of the this case B of case S1. So this one corresponds to this polynomial. So now we take this sum of all of them for any. So it starts with the inferior intersection point. It doesn't come with any T. And you have an intersection in the coordination 1 corner, you have a 1 T. And the coordination 2, you have a 2 T. Blah, blah, blah. And so you can go on and you get this chain complex. And after this, I think it is better. I can safely say, at least as a conjecture, it means that we can generalize these constructions of boundary class to this situation so that this becomes a chain complex. So that's really the natural Freire theory for this simple normal Gaussian divider. But I think I omitted one important point. It's a following. So this is a Freire theory in other general spaces. So as you know that even in a smooth case, to define Freire homology, there is a problem about the disk value. So you have to study this disk value. And so in this case, you have to consider this CF of L and L. And there is some difference because you have this D. And then you have this L1 and L2. I think this is L1. You have this theta. And this theta, I assume to be non-zero. So if you consider this split, then you have this kind of, you have all this, so something like that, nothing is zero, positive or negative. So you can just split them to positive string and negative string. But in a case, this is L1 is equal to L2, this angle is zero. So you have to think something about what happens in a case that L1 is L2 and this angle is zero. So you have this some external component. But I think the way to handle this whole thing, so L1 and L is actually not transversal. They are both bottomless. So you have a cycle, you have a kind of, critical summary for which is Eric cell. It lies on X. But then this point is just a boundary point. So this cycle step goes to this point. So you can get that. So first of all, you can just take this L node and then the limit is the case like that. So that's the way I expect one can handle this one. So the conjecture is that this gives some empirical structures, and then you can use boundary constraint to get the theory in this way, and you need normal crossing divided cases. So that's the normal crossing divided cases. And actually, we know something with in the paper that we know this kind of other conjectures. So yeah, that's what is normal crossing case. Any questions at this stage? Okay, so now I want to go something a bit novel. So now I want to consider this so more general case. Yeah. So I want to consider the case of more general torch similarity. So I want to recall what was the torch similarity. So I think you know many of you know torch geometry maybe better than me. Let me explain something. So because the n it is a n-dimensional lattice, n n-dimensional pre-abelian cube, and nr is just tensor to r, and m is a dual, and nr is tensor to r. I think this is the standard name. N and m is standard name because I can check it. So now I want to consider sigma. It is a rational complex form. It means that it is generated by integer vectors and it's attached in some kind of form. And this is a fun. So now I want to consider its dual. Dual is a set of x, so that its inner product with any element of this sigma is non-negative. It is a complex form on this M. It's a dual form. So and then because there's sigma checker M, so this is something like a finite generated monoid. And beta 1 to beta M is a generator of this monoid. Any element of sigma checker M is written as a non-negative linear product, linear combination of this beta I. So this is usually done in a geometry. And then, so this new sigma, which is some kind of toric macro associated with this fun, is a scheme of this ring. So ring is because this is a finite generated in the semi-group, abelian semi-group. So this ring is a commutative ring, and people take spectrums. That's a ring new sigma. And so this is a toric macro, and to see this toric macro more precisely, more detail, you take this macro, you sigma to 6 to the power m. M is the number of this beta, so that p is a multiplicative mark from this semi-group to C. This corresponds to the point of this scheme. Then p goes to the, you can just associate the value of beta m p, you have the element C here. So this is a embedding of algebraic and its image is written by the following equations. So if you have any m integers, so that beta j is not linear independent. M is usually bigger than n. So you have any linear relation among beta j. And then this x m is the image of this map. Even only if the I'm sorry, I forgot that. Sorry, yeah. Xj alpha j is equal to xj minus alpha j. Yeah, I forgot. So this kind of equations. So this is the this is xj to the power alpha j, and this is xj to the power minus alpha j. So this is the equation to define the sigma. So that's very standard toric geometry. I just copied from Fukwa's book. So this is your sigma. So then the our symplectic manifold has no singularity, even only it looks like locally, just your sigma times some complex vector space is a natural simplex structure. So now, so I have to ask myself the following question. So let us suppose the X is it has this toric singularity, it has a symplectic form. So what kind of simplex structure, what kind of Lagrange submanifold is natural to consider in this symplectic manifold to study layer theory? So that's my proposed answer is the following. So we consider L submanifold, which looks like locally K sigma times some Lagrange submanifold of Ck in this neighborhood. So K sigma is some Lagrange submanifold of U sigma. So I want to explain what kind of K sigma I want to consider. So what was my proposal is following. So U sigma is a toric manifold. So it has a theta n action. And we assume K sigma is invariant of R plus n actions contained in the theta n action. So that's very similar to the case of smooth or normal cosmic divisors. So I can make it more precise in the following way. So the K sigma is a moment for K, but then this is the theta n action. So you have a moment map from your sigma to somewhere, and so the moment map in this case it just go to okay. So you have a moment map on your sigma, and the image is actually sigma dual in MR. Sigma is a fun, so moment corridor is a dual. So you have this moment map, and of course the moment map this moment map is a quotient of your sigma by this S1 n image tori. So this R plus n is something like orthogonal. So this K sigma is actually isomorphic to this moment. By moment map to this sigma check. So this assumption is just so you have the submanifold in this toric singularity, so that in the neighborhood of this singular point, it is something like identified with the moment corridor, and it's kind of invariant by this R plus n actions, which is also now with this x1 to power n actions. So more precisely, let us stratify our X toric singularity as a union of X sigma. So X sigma is a point of P, so that its neighborhood is the neighborhood of 0 of your sigma plus some opposite of Ck. So this is a very natural stratification. And then we require L, so that L cap X sigma is a Lagrange submanifold of X sigma. So X sigma, at least in interior, is a smooth complex manifold, and it has scalar structure. So we assume it's a Lagrange submanifold. And then for any P of L sigma, the neighborhood of P n is this sigma dual, which is equal to the sigma times some K dimensional Euclidean space. So this is the K, Ck, and this is now in a sympathetic sense. So then this L is not a manifold with formats. In the case of normal cosmic divisor, it was a manifold with formats, but it is not so terribly bad because it is locally so this is a complex polygons. So it's something like a space which is locally a complex polygons. So it is a bit more general than manifold is boundary, but very similar to manifold is boundary. Okay. But then if you look this previous definitions, yeah. So here goes let us suppose the X is equal to normal cosmic divisors. And such an object can be imagined as a kind of space with toric type singularity, because in this case sigma is just a very natural form, which is a product of non-negative real numbers. So you just apply this definition I just explained. In this case, then this L is exactly the assumption I assume. In this case, in that case, it means that L is the manifold with corners, and for the major K corner correspond to intersection with the K divisor. And then as I mentioned before, actually I was trying to run this Barker theory on exploding manifold. I mean, just before I came here, I was in Japan, and I gave 3 or 4 talks, 4 lectures about exploding manifold. I didn't understand everything, but yes. So I know a bit about exploding manifold, and this definition seems to be fit to the field story. So let me review a bit on this Barker wrote about exploding manifold and how we can try to modify it. So he goes to something like this, C to the P to the power R, this is called explosive stability. Its element is this kind of expression. So C is a complex number, and P and the P is some variable. And so it is unrelated to P, which I introduced to us. It's just a variable. And we have this lambda. And so the totality of this kind of expression is this 70. And the product is just like this, just a take product like this, 0 and this. And the sum is rather interesting. If lambda 1 is smaller than lambda 2, only we have this. And if lambda 2 is smaller, we have only this second term. And if equal, then this coefficient we can take some. So this is the proper setting. And then how he define this set B of sigma? The sigma is a rational convex form in Rn. And he considers this N2 of this element of this Brook setting. So that this each of Ci is just not zero complex numbers. But this you take this lambda 1 to lambda n as an element of Rn. Here the coordinate is contained in this convex form. So this is the theoretical kind of local model of exploding manifold. And he defines some functions. The function is just a map from this space to this exploding semi. It is actually in this case it is just a I component of this. So that's a kind of, you have any functions. And that is the kind he said, the coordinate functions. And what is important from this in our story is that something which Barker called smooth path map. It is a map from the sigma to c to the power m. So m is for this sigma fun because the beta 1 to beta n. So that sigma is defined. Sigma is defined. Sigma is equal to this lambda beta j. I think this is something I mentioned before when I reviewed the talk. So we take this beta I and we use it to define the sigma to c to the power n. So you have this c to lambda I, and then just equal to xj coordinate. And his definition is that this xj is 0 if this strict inequality form. So let me record that here. So the definition of the sigma is that this guy is non-negative yj. So if this is a strict inequality form, then it just xj just defined to 0. And if it is 0, then it is something like a ci beta ij. This is xj. This is a strange definition, but one can keep look that in this case is the new sigma, that is the local toric singularity, is the image of this smooth path map. So this exploded manifold is something like this new sigma together with some more interesting structure. And I want to explain that this one is very much compatible with what I tried to explain. So this is very compatible with sigma. I just wanted to out. I just want to require most of the same thing, but let's CI is just a positive here now, in place of non-zero complex numbers. Then we consider the image of this sigma r, and it is very easy to see it is this sigma. It is this Lagrange summand. So it means that in this Brett-Farkas definitions, if you will consider just a real part, we get this Lagrange. So one may say that this real part of exploded manifold is our Lagrange. Okay, so now this is the problem. I want to solve it. So I think Brett-Farkas studied this Homological curve from closed Riemann surface to this exploded manifold, and he proved that it has again some kind of pyramid structures which is locally looks like exploded manifold, and he defined Bartel fundamental class of such a modular space, and that's his definition of Gromov-Witten theory in exploded manifold. So suppose we have the Lagrangians, which is something like a real analog of exploded manifold. So we might try to study Homological disk or Homological strip in this settings, and we can try to define partial fundamental chain for such a strip, and we can do it. I want to think that it gives this big structure and gives this category associated to this exploded manifold with simple structures. So that's a problem. And I think I can do something in the case, at least in the case of simple non-crossing dividers. In this case, there is manifold corners. And something I don't know is that what Brett-Farkas basically did is that he defined a notion of homomorphism between exploded manifold, and then the compactification of modular space of homological exploded manifold is just defined in a sense that some kind of homomorphism of exploded manifold from some normal crossing stable curve, semi-stable curve, and that's nice definitions. But then we want to try to see what is definition of space. Then it is something like one can define something very much equivalent in a very combinatorial way. You have several Riemann surface, so that each component, some component go to X, or some component go to inside of some divisors, and then they have some compatibility conditions, blah blah blah. We can rewrite the conditions in that way. And actually, Mohamed Kefrani wrote some papers about compactifications in the case of smooth normal, in a case of simple normal crossing divisors. And it seems that what Kefrani defined using this kind of down-to-earth combinatorial way is very much related to this Brett-Farkas definitions. And I hesitate to say that it is equivalent, but it could be equivalent. So, and I'm not so much sure whether one can use this language of exploded manifold and its real versions to define compactifications of homological disk moduli with this Lagrangians using that kind of language. But at least I believe that there is some combinatorial definitions which give some compactification of the modular space of disks, and that compactification has some nice project on the class that we want to think about. Then I think I want to explain a bit more and want to finish, maybe to finish a bit earlier is welcome in this after 6 talks. So now I want to explain this. So I just explained this some class of Lagrange manifold, and this Lagrange manifold seems to be related to the So this is a Miller-symmetric component. So I want to consider this family from script X to D2. So it's a kind of one family of complex manifold. And assume that the fiber in epsilon is a smooth manifold for epsilon on 0. Maybe you may imagine that it is a Calabian manifold. And then we consider this total space has toric singularity, and M0, the fiber of 0 is a singular. And I think this is a case that studied by many people. For example, I think Gross and Ziegler proved some reconstruction theorems And what they obtain in that way is exactly this kind of situations. They have toric singularities and sometimes the toric singularities can be forms to give a family of carrier mind. And in a simplest case, like you consider this maximal generation of the critic surface or something like that. Then in that case, this singularity is just a simple normal singularity. So this is very much natural relations. Then what I want to say that okay, so now I want to consider this command of L in this total space, and which satisfies this assumptions I assume. I mean, locally it looks like a moment particle. And then my claim is that in this case, this L seems to give this Lagrangian sections of the associated XYZ vibration. So I want to explain it. So you know, this is in some case. I mean, suppose that suppose that this is a maximal generation family of Carabia manifold. So MF shell Carabia, and then the origin is some singular thing, and it is suppose we assume that maximal generations. Then it is expected that it gives this XYZ vibration. And what is the basis of this XYZ vibration? I think it is natural. Yes, a natural answer to the policy. So we consider, suppose that there are 5 elements. So in this particular fiber, we consider the point P, which lies in the deepest strata of the singularity. It means the following things. The neighborhood of P is some U sigma P, and the 0 is corresponds to P. I mean, usually our assumption is that the neighborhood of P is some U sigma P cross some Euclidean space. So, but P is the deepest strata. It means that this Euclidean part is nothing. You have just and the toric singularity. And you know, this total space is n plus 1 dimension. The sigma P is the cone of n plus 1 dimension. Then we have this moment particle, and moment particle is the cone. So we divide by this cone, we have a rational polygon in n dimensional polygon. So I mean, the situation is something like this. And P is somewhere here, and then you look this neighborhood, and then this neighborhood looks like a toric manifold, and you take this polygon, toric moment particle with a cone, you just take this boundary. It's a n-dimensional polygons. So I want to group these polygons in a following way. So if Q is also such a point, you have another polygon, P of Q, right? Then you get the first R, which join P and Q in a one-dimensional strata. Then we get this direct point of R of this path. Then the neighborhood of R looks like using R plus C. You know, this is not in the deepest strata. It's a two-dimensional strata. They are two-dimensional strata. So this guy is the toric singularity and cross C. Then you take this P of R, it's just a kind of moment particle divided by R plus. Then this PR is actually a plate of this P of P and P of Q. So we group P of P and P of Q along P of R. So we do this kind of grouping, and we take all P of P and then group in this way. And there are some bad cases which is called non-basic. In the basic case, it gives a good nice grouping, and you get a polygonal complex, n-dimensional polygonal complex. And I think it is expected that this polygonal complex is the basis of SYZ validation. So, and SYZ validation locally looks like this moment. You know, you have this kind of maximal generations. Then the part which corresponds to the regular fiber is most likely to the neighborhood of the point of deepest strata. Then on the deepest strata, you have the moment mark, whose fiber is Tn. So this is the SYZ validation. So that I think is something expected. Okay, so now what is our choice of L? So our choice of L gives this moment particle itself in the neighborhood of each strata. So you just look at how this L goes, and we take this L cap in epsilon. And this goes to B. And this is actually, so this is actually sections. So the section of this differentiation corresponds to the Lagrange sum code that I believe I just explained. This is not a theory, so please don't believe me so much. But then I want to include that, so but then you know, this gives some Lagrange sum code. So I want to include more Lagrange sum code. For example, I need to understand this as well as fiber. So in this case, we have some different. So you know this in this Fuqua type things, this texture corresponds to the case Pi is a positive real number. But in place, you can just take this Pi is S1 in S1. That corresponds to this SYD fibers. So you have some intermediate situations, so that in this moment polytope, you take some flat subspace and you take a unit for normal. So some direction flat, some direction S1. There's other cases, and probably there are more complicated cases where there are kind of some interactions in a moment polytope. That I don't know. So I believe that one can try to generalize the Lagrangians which include this kind of cases, and still we can define preassembly. But that's the wrong way. So, but I think I believe we can do it. And probably we can try to kind of use gross liver type constructions to and then prove homological mirror symmetry in that case. That's a proposal. That's okay. Thank you very much.